Welcome back to our channel, and thank you for joining again. I'm Semi Sherpa, your navigator on this fascinating expedition through the complex world of semiconductor technology. Our photolithography series has returned, enhanced with richer detail and a broader range of examples, so you can build real confidence step by step. Mastering the ideas in this series will prepare you to follow specialized lectures, to read academic texts with clarity, to participate in professional conferences, and to hold productive conversations with practitioners in the field. Whether you are an experienced engineer, a curious student, or a newcomer to the semiconductor industry, this series is designed for you. Our first episode focuses on the track process, with a clear emphasis on coating and development of photoresist. Exposure technologies such as EUV lithography often capture the spotlight, yet a complete and reliable photolithography flow depends on a precise understanding of the track process. Here is how we will proceed in this episode, with a smooth path from one step to the next. First, we examine the coating process, including HMDS vapor prime for surface preparation, spin coating to form a uniform film, and post-apply bake to stabilize the resist layer. Next, we move into the interface process between track and scanner tools such as WEE, BST, and PIR. Finally, we enter the develop process, covering post-exposure bake for acid diffusion tuning, the develop step itself for pattern formation, and hard bake for final stabilization before inspection and subsequent modules. By the end of this episode, you will understand why each operation exists, how it links to the next task, and how small parameter choices add up to large gains in yield and line-wide consistency. Stay with me, focus on the logic behind every decision, and you will be able to apply these concepts in real production and research environments. Are you ready to explore the track process in depth? Let us begin. Please note that my content is exclusively for YouTube, and any uploads found elsewhere are unauthorized. Each video is meticulously crafted, akin to the precision of silicon wafer fabrication, involving a month-long process with late nights and ample coffee. Discovering my content on platforms other than YouTube is disheartening and impacts my motivation. Supporting the idea of open knowledge sharing should not be mistaken for allowing the redistribution of my content elsewhere. Your understanding in upholding creators' rights is appreciated. This is the first episode in our photolithography series. Thank you for being a member of this channel. Just as a chip needs a circuit, we thrive on your support and cheers. Give us a thumbs up like you would a successful chip yield, and ring the notification bell so you will not miss our electrifying content. Do not forget to show extra appreciation with a super thanks. It is fuel for our creative journey. Now, are you ready to jump? Photoresist is ready. Track tools are online. Coating boost. Arf arf arf. Bow wow. Yip. Light speed. In this slide, I'll explain what photolithography means, where the term comes from, and how it evolved from stone printing to silicon patterning. Photolithography, often called photo, is a core process that forms intricate patterns on silicon wafers. The word litho comes from the Greek word lithos, which means stone. Stone lithography began in the year 1796, when Alois Seinefelder prepared a smooth stone, drew an image on its surface, rolled on ink, and pressed paper to transfer the design. Artists and printers relied on the stone as the plate, on ink as the medium, and on paper as the final target. Modern photolithography keeps the same idea, but replaces the tools with precision optics and materials. The plate becomes a photomask or a reticle that defines the pattern. The medium becomes light that is shaped and reduced by projection optics. The target becomes a wafer coated with photoresist that captures the aerial image. We coat the resist, we expose it with patterned light, we develop the resist to reveal the features, and we transfer those features into the film below through etching or through implantation. This shift from stone and ink to light and resist enabled the semiconductor era. As circuits demanded smaller and denser features, photolithography delivered systematic miniaturization with repeatable control of line width and overlay. In the span of a few decades, printing moved from the art studio to the cleanroom, turning a printmaking method into a precision engine for manufacturing. That journey, from artistic expression to technological patterning, shows how a familiar concept can be reinvented to push new limits in science and industry. This slide, familiar to anyone in semiconductors, shows the 8 key steps of photolithography. Let us briefly review them to refresh our memory. 1. Vapor prime. The wafer surface is made hydrophobic by a dehydration bake and HMDS vapor treatment, an adhesion promoter. This ensures even resist coating and provides the foundation for the layers to come. 2. PR coating. A photosensitive organic material, the photoresist, is dispensed and spread by a spin coater. This film is essential for later etch and implant modules, setting the stage for precise patterns on silicon. 3. Soft bake. This bake removes roughly 70 to 80% of the casting solvent from spin coating. It improves adhesion, improves developer resistance, and sets photosensitivity for exposure. 4. Alignment and exposure. The wafer is aligned to the underlying pattern using alignment keys. UV or EUV light passes through the photomask or reticle and forms a latent image in the resist. 5. Post-exposure bake. This step drives the chemistry that distinguishes regions that will dissolve during development. Depending on the resist type, reactions such as photoacid diffusion or deprotection occur. 6. Develop. The regions chemically modified to dissolve are selectively removed by the developer. Both positive tone development, PTD, and negative tone development, NTD, are used in practice. 7. Hard bake. The remaining resist is hardened or cured so the pattern withstands etching, preserving design integrity. 8. Inspection. Critical dimension targets and overlay accuracy are checked. If results fall short of specification, rework such as strip and recoat is initiated, reflecting strict quality control. In this slide, I explain the wafer coating flow before exposure and the film stacks used for KRF, ARF, and immersion ARF. We will follow the modules shown here, from ADH and CPL through BARC, PR, TARC, ITC, and SOB. Wafers arrive from the carrier station block, CSB, and enter coating. ADH is the adhesion step. We run HMDS vapor prime after dehydration to make the surface hydrophobic and to improve resist adhesion, so the photoresist pattern does not collapse after development. The chilling plate, CPL, cools the heated wafer to the target temperature. The multiple CPL icons indicate intermediate cooling between coats. After each spin coat, the soft oven bake, SOB, removes solvent and stabilizes the applied film. For KRF, the typical stack is ADH followed by photoresist. Depending on the sublayer, ADH may be skipped when adhesion to the underlying film is already sufficient to prevent pattern collapse. For ARF, the stack uses BARC, photoresist, and TARC. BARC, the bottom anti-reflection coating, controls reflectivity by tuning refractive index and absorption. It suppresses standing waves and notching, improves PR adhesion, and helps leveling. The BARC bake temperature exceeds 200 degrees Celsius and produces noticeable fumes. Because BARC adheres well to the underlayer, the ADH step can be omitted. TARC, the top anti-reflection coating, is applied on top of PR. First proposed by Hitachi in 1991, it is selectively used on some logic layers that must remain open, such as ion implantation layers, to control reflection. In immersion flows that use TARC-less PR, this top coat can be omitted. For immersion ARF, the sequence is BARC, photoresist, and ITC. ITC, the immersion top coating, protects the resist from water contact. It prevents scanner contamination from leaching, blocks water penetration into PR, and reduces bubbles and watermarks. ISP, immersion-specific PR, can be used as a top coat less resist in this case. These coating steps prepare a stable, low-reflection stack for exposure and maintain pattern integrity through the downstream modules. We will discuss the materials behind each film in a later episode. In this slide, I explain HMDS vapor prime and the ADH station of the MPB module on a track tool, why we run it, and how we protect the sealing area and monitor chemistry. The MPB handles chemical storage and conducts the adhesion, ADH, process. HMDS vapor prime converts the wafer surface from hydrophilic to hydrophobic, strengthens photoresist adhesion, and helps prevent pattern collapse after development. The ADH step operates as a single wafer, CVD type process. Each wafer loads and unloads, so the lid opens and closes repeatedly. This motion rubs the O-ring at about 180 degrees Celsius, causing thermal wear that can lead to vacuum leaks. To avoid damage, we keep HMDS away from the O-ring region and use an N2 curtain to shield the seal during the ADH cycle. Hexamethyldisilazane, HMDS, is a colorless liquid with a boiling point near 125 degrees Celsius. We apply it by vapor priming rather than liquid, because the gas phase allows higher reaction temperature and cleaner surface silylation. The wafer backside is also primed, which can help suppress unwanted wet etch on the backside during coat and develop. At room temperature, HMDS has a vapor pressure of about 20 torr. We can pump the chamber to roughly 1 torr, then admit vapor from a vessel kept under vacuum, or we can bubble an inert carrier such as N2 through heated HMDS and feed the vapor into a heated vacuum chamber. Storing HMDS under vacuum or under nitrogen extends its lifetime by preventing reactions with atmospheric water and oxygen that cause decomposition. An ammonia-like smell is a warning sign of degraded HMDS. For quality control, we monitor HMDS level with a dip-type sensor, reading high, high-low, or low-low, and we compare upstream, tank, chamber, and exhaust sensor signals as shown in the diagram. Together with O-ring protection by the N2 curtain, these controls maintain vacuum integrity and stable adhesion performance. In this slide, I explain the ADH surface treatment, how HMDS vapor prime converts a hydrophilic wafer to a hydrophobic wafer, how we tune that hydrophobicity, what overpriming does, and why ammonia byproduct matters. The goal of ADH is simple and crucial. We run HMDS vapor prime near 180 degrees Celsius to make the surface hydrophobic, enhance photoresist adhesion, and prevent pattern collapse after development. We fine-tune the result by adjusting HMDS flow, temperature, and process time. Photoresist polymers do not naturally adhere well to silicon-based films used in fabs. HMDS forms a thin silylated layer that blocks water attachment and reduces developer undercut during develop. This adhesion promotion is standard for silicon, silicon dioxide, silicon nitride, and other common device films. The sequence begins with thermal dehydration, typically between 100 and 200 degrees Celsius. Dehydration alone cannot fully remove surface water on silica substrates. We complete the job by chemical reaction with an adhesion promoter such as HMDS, usually at about 180 degrees Celsius, for roughly 60 seconds. At the surface, silicon atoms bind water to form silanol groups, SiOH. We must replace the OH group with an organic functionality that bonds well to photoresist. Alternatives include other silanes or a dilute HF dip to generate hydrophobic SiH or SiF surfaces, but in practice HMDS vapor prime is the most common and effective, yielding hydrophobic trimethylsilyl groups. Wettability links directly to surface energy. A useful rule is that if the liquid surface tension is about 20 dynes per centimeter higher than the solid surface energy, wetting will not occur. HMDS treatment lowers the effective surface energy of the solid to better match the organic resist. We monitor this by a water contact angle test on a primed wafer. Hydrophobic surfaces show larger angles, hydrophilic surfaces show smaller angles, and properly primed wafers typically measure around 50 to 70 degrees. Be careful with overpriming. While it can keep resist from washing off during develop, it may reduce true adhesion to the substrate. Symptoms include partial non-coverage, delamination, or popping during exposure. Mitigations include shorter prime time, using a lower surface tension resist solvent, pre-rinsing the wafer with the casting solvent before coat, and light oxygen or ozone plasma treatment. Finally, HMDS reactions generate ammonia, NH3, as a byproduct. In an inline configuration, this gas can diffuse toward the exposure tool and cause side effects. On the next slide, we look at controls to manage and contain this ammonia. Continuing on, I'll explain 3 representative defect mechanisms linked to the ADH step, focusing on HMDS byproducts and their effects on resist, reticles, and scanner optics. Case 1, the post-exposure delay, PEE, effect in car-type resists. Exposure generates photoacid from the photoacid generator, PAG. When the wafer returns to the track for develop, residual NH3 in the atmosphere can neutralize that acid. The loss of acid slows deprotection and produces resist defects such as slimming, T-top, and footing. NH3 originates from HMDS reactions and can linger inside the track, and HMDS itself behaves as a basic amine. Mitigations include using a base quencher in the resist as a buffer to stabilize acid concentration, configuring exhaust to prevent backflow, and continuously removing NH3 with chemical filters. Case 2, Reticle Haze. With KRF adoption, the track and scanner commonly run in line, so byproduct gases from the track can enter the scanner. NH3, water, and sulfur oxides react under deep UV to form ammonium sulfate-type deposits between the pellicle and mask surface, creating on-pattern haze and shortening reticle cleaning cycles. Countermeasures include stronger reticle cleaning, flow direction from scanner toward the track, and tighter control of amines and SO2 in the interface. Case 3, Lemma lens contamination. HMDS that meets moisture can form siloxane species. Under deep UV energy, these break and convert to SiO2-like deposits in a photo-CVD-like process. The result is continuous SiO2-type contamination on optical elements, exposure drift, and LER degradation, often requiring costly lens replacement and long downtime. Therefore, strict control of HMDS fumes at the ADH module is a critical management item. These 3 cases show why ADH byproduct control, exhaust design, and chemical filtration are essential to protect resist performance, extend reticle lifetime, and keep scanner optics clean.
In this slide, I'll explain the coating unit, the key hardware inside it, and the process sequence, including RRC pre-wet, resist dispense and spin, edge bead removal, and DFT nozzle standby. The coating unit includes a spin chuck with 3 lift pins, a resist nozzle block also called the resist arm, an EBR nozzle block or EBR arm, a DFT, dry-free tech tank, an exhaust duct, and the bowl or catch cup. When a wafer arrives, the lift pins place it on the spin chuck. First we run RRC, resist reduce consumption. A dedicated nozzle dispenses thinner to pre-wet the surface, creating a solvent-rich film that conserves expensive photoresist. Next the resist arm dispenses PR. The wafer spins at high RPM, and centrifugal force spreads the resist to a uniform thickness across the wafer. Then we perform EBR, edge bead removal. A solvent jet from a nozzle tilted outward at about 45 degrees rinses the edge and bevel to remove the thick bead formed by surface tension. Although not shown in the video, EBR and a back rinse are also applied to the wafer backside. Tool layouts vary. One resist arm may serve 1 to 4 coating cups, while each cup has its own EBR arm. Between shots, the resist arm waits in the DFT tank, a thinner saturated enclosure that prevents nozzle drying and clogging. Typical nozzle configuration is 10 PR nozzles, 1 RRC, and 1 improved RRC. Together, the spin chuck and lift pins ensure accurate placement, the pre-wet step saves resist, the EBR removes edge defects, and the DFT standby keeps nozzles clear, matching the components labeled on this slide. In this slide, I will explain how we set and control photoresist thickness, TPR, during spin coating, including target selection, swing curve effects, viscosity and spin speed scaling, and in wafer uniformity tuning. First, define the target TPR. It must satisfy the post-develop aspect ratio without resist collapse, meet downstream dry edge selectivity with the underlayer, and sit in a thickness region that is insensitive to swing curve. About the swing curve. Line width or reflectivity varies sinusoidally with resist thickness because incident and reflected light interfere constructively or destructively. We therefore choose a thickness insensitive zone for both isolated and dense patterns to reduce swing-related bias. Once the target thickness, sometimes written as HM, is set, spin coating controls it mainly by viscosity and spin speed. Simple scaling shows that thickness increases with viscosity and surface tension and decreases with density, radius, and spin speed squared. In practice, viscosity sets the central value and spin speed trims the result. 1. Viscosity. Stronger molecular friction resists centrifugal thinning, so higher viscosity gives a thicker film. We tune viscosity by the solvent to solids ratio, and the final thickness is roughly proportional to the liquid resist viscosity. 2. Spin speed. Faster spin makes the film thinner, approximately following an inverse square root with respect to speed. Operational limits apply. Below about 1000 rpm control is poor, while excessive speed can introduce turbulent airflow that degrades uniformity. For 300 mm wafers, a practical upper limit is around 2000 rpm, subject to the resist and solvent system. Choose viscosity to land near target and use the final spin to fine-tune within roughly 10%. Now, uniformity tuning across the wafer. To increase center thickness, raise PR temperature, increase center evaporation, or increase center side viscosity. To increase edge thickness, raise cup exhaust, increase edge evaporation, raise edge side viscosity, increase dispense RPM, extend dispense time, or lengthen reflow time. Finally, equipment environment. THC, temperature humidity control, holds about 23 degrees Celsius and 45% relative humidity for process stability. Differences in exhaust volume can still create tool-to-tool variation, so precise flow control and calibration are required to maintain both target thickness and uniformity. In this slide, I'll explain resist dispense strategies in the coating unit, static dispense, dynamic dispense, and RRC, and how RRC reduces photoresist usage while keeping film quality. Please refer to the timing chart and the good and bad examples shown on the slide. First, static dispense means we dispense while the wafer is not spinning. This can lower suckback-related defects. However, it often causes center thickness non-uniformity and heavy bowl contamination. Next, dynamic dispense means we dispense while the wafer is spinning. This improves spreading and thickness uniformity. The trade-off is higher resist usage and a renewed risk of suckback at the start and at the end of dispense. Because photoresist cost ranges from low for non-critical layers to very high for advanced nodes, reducing usage is a key objective. During spin coating, most of the liquid is thrown off by centrifugal force. The practical goal is to lower the dispensed volume while keeping uniform coverage and low defectivity. RRC, reduce resist consumption, achieves the goal with a thinner pre-wet, also called surface conditioning. The sequence follows the graph. Start with low RPM for RRC dispense. Hold briefly for PR reflow. Ramp to the PR dispense speed. Run at high RPM for spreading. Finish with EBR and back rinse. The solvent-rich pre-wet lets a smaller PR dose spread smoothly to full coverage. Compared with a conventional flow, RRC can reduce car resist usage to about 37%, and an improved RRC with thinner sweep can reduce it to roughly 13%. RRC has its own considerations. It increases thinner consumption and demands strong motor torque. Poor dispense conditions may introduce bubbles, so small accurate doses require high-performance pumps and careful timing. A common failure mode is fingering near the edge. This occurs when the RRC solvent has much lower surface tension than the resist and weakens the advancing front. Countermeasures include choosing an RRC solvent that increases PR solubility without overly lowering surface tension, tuning dispense temperature and sweep, and minimizing the delay between pre-wet and PR dispense. In summary, moving from static to dynamic and then to RRC balances uniformity, defect control, and material cost. With tuned parameters, RRC delivers smooth spreading with far less resist, exactly what this slide highlights. In this slide, I'll explain edge bead removal, EBR, and the hump issue in coating. We'll also look at why edge beads form, how EBR cuts them cleanly, and how to prevent hump-related defects. Edge beads form because centrifugal force thins the film while surface tension pulls liquid inward near the rim. The result is a resist ridge at the edge, typically in the outer 1 to 2 mm, and it can be 10 to 30 times thicker than the main film. This ridge causes particle shedding when gripped, poor chuck contact and heat transfer, and longer dry and strip times, so we remove it during spin coat. EBR uses a resist solvent sprayed at about 45 degrees outward while the wafer spins. The angled jet dissolves the rim without splashing onto the top surface, and a back rinse protects the backside. To increase usable dies, fabs continually narrow the EBR width, tightening control from about 0.7 plus or minus 0.3 mm toward about 0.5 plus or minus 0.1 mm. EBR cut accuracy depends on hardware repeatability. Key factors include the resist arm position repeatability, its adjustment precision, and wafer placement repeatability. Spin coat errors also come from the EBR arm position determination and from wafer misalignment introduced by the 3-lift pin operation. The hump issue appears most often with spin on hard mask rather than with photoresist. When the EBR solvent does not dissolve well in the hard mask, the rim swells as solvent is absorbed. Later layers deposited over the swollen rim can tear, which we call hump tearing, and heating can make the swollen zone pop. Using a specialized thinner with better compatibility reduces swelling and lowers hump height. The photos on this slide compare a clean EBR cut with a bad case that shows a raised rim. With tuned angle, flow, and arm positioning, EBR removes the edge bead while avoiding hump and keeps the wafer ready for downstream steps. In this slide, I'll explain nozzle tip management in the coating unit, with a focus on PR suckback control in the DFT tank. First, PR suckback. After a dispense, a small meniscus of resist remains at the nozzle tip. If the pump does not draw that meniscus slightly back into the nozzle, a drop can fall on the wafer and create a defect. The suckback action pulls a controlled volume upstream and holds the meniscus inside the tip. Too little suckback allows drip and stringing. Too much suckback can entrain air, create bubbles on the next shot, or disturb the dispensed volume. The optimum value depends on resist viscosity and on the surface tension between the liquid resist and the nozzle material. The sketches on the left show no or inadequate suckback, proper suckback, and excessive suckback. Next, the DFT tank, also called dry-free tech. When the nozzle is idle, it parks in a chamber filled with thinner vapor. After a shot, the tip returns home, purges a small amount, performs PR suckback, and then stays in the vapor so the tip remains wetted rather than drying. This suppresses solvent emission to the room, prevents nozzle tip contamination and PR hardening, and reduces dummy dispense and cleaning tasks. In the resist arm block there are 10 individual nozzles, and each nozzle can run its own DFT sequence. The center photos illustrate a normal tip, a PR suckback state, and a thinner suckback state inside the DFT chamber. Together, precise suckback control and DFT standby keep dispensing stable, protect the wafer from stray drops, and keep the nozzles clean for the next coat. In this slide, I will explain how photoresist moves from the bottle to the coater, how the Iwaki tubofram pump meters the liquid, which materials are used in contact parts, and how suckback prevents stray drops on the wafer. The flow starts at the PR gallon bottle inside the MPB. Nitrogen provides head pressure and pushes resist to the reservoir called the L/E tank or to a buffer tank. The L/E sensor reports when loading or emptying is required so the bottle can be replaced without stopping the line. From the tank the liquid passes a trap and a bubble sensor, then enters the pump, then a final filter, and finally the nozzle at the coater. All wetted parts use fluoropolymer materials such as PFA or PTFE for chemical compatibility with the resist. The Iwaki tubofram pump uses a bellows that works like a piston. On the suction stroke the bellows expands and draws resist through an inlet check valve. On the discharge stroke the bellows contracts and sends a defined volume through the outlet check valve toward the nozzle. This design gives very precise and repeatable shots with minimal dead volume and low particle holdup. For EUV and organic resists, the drive gas for the bellows is nitrogen rather than air, because air can permeate fluoropolymer parts and introduce moisture that would damage the resist. The pump also performs suckback. After each dispense, a small meniscus remains at the tip. The controller pulls a short reverse volume so the meniscus sits inside the nozzle. Too little suckback allows a drip. Too much suckback can pull in air, create bubbles on the next shot, or disturb the metered volume. The optimum value depends on resist viscosity and on the surface tension between the resist and the nozzle material. With this path, precise metering, compatible materials, and controlled suckback, the spin module delivers defined and reproducible resist volumes to every wafer while keeping the wafer surface clean. In this slide, I'll explain point-of-use filters for photoresist dispensing, why they are needed, how they work, and how requirements change as feature size shrinks. Resist cannot be made perfectly clean at the factory, so we filter it at the point of use inside the pump path to deliver a defect-free shot to each wafer. Packaging filters the liquid to roughly 1/2 to 1/3 of the critical dimension, which today reaches about 10 nanometers and below. Very small pores are hard for polymer solutions to pass, especially below about 50 nanometers. Even so, point-of-use filters with pore ratings under 5 nanometers are used when needed, with special designs to keep flow stable. There are two main capture mechanisms. Sieving uses size exclusion, so smaller pores catch smaller particles. Non-sieving relies on adsorption, so impurities smaller than the pore size are trapped on the pore surface. The left graphic shows the shift from sieving to non-sieving as nodes move from KRF and ARF dry, to ARF immersion, and then to EUV and DSA, where complex impurity removal is required. The right panel shows a typical photoresist point-of-use filter used in the coater. The takeaway is simple. Point-of-use filtration is essential for clean dispensing. As features shrink, filtration moves beyond pure size exclusion toward adsorption-based designs to meet more intricate demands. In this section, I will explain the soft bake step, also called PAB, what it does to the fresh resist film, which materials need higher temperature curing, and how we choose safe conditions. After spin coat, the resist contains about 20 to 40% solvent by weight. Soft bake removes this solvent and densifies the film. Typical conditions are 90 to 120 degrees Celsius for about 60 seconds on a hot plate, followed by a chill plate to equalize wafer temperature. Most casting solvents boil near 140 degrees Celsius, so a proper soft bake leaves roughly 3 to 8% residual solvent to stabilize the film before exposure. Different materials need different temperatures. BARC and spin on hard mask require high temperature curing around 200 to 215 degrees Celsius, and sometimes up to about 240 degrees Celsius, to harden fully. Photoresist itself uses the lower soft bake window, commonly 95 to 105 degrees Celsius, to set adhesion and developer resistance without damaging the chemistry. If we skip or underbake, the film keeps a high solvent content. For positive resist, the develop rate becomes too high and can vary with time as solvent slowly evaporates, which changes line width and profile. The SEM images on the left illustrate good versus inadequate bake results. Why bake at all? Removing solvent reduces thickness, improves adhesion, makes the surface less tacky and less prone to contamination, and sets the film for the next steps such as post-exposure bake and develop. There are limits we must respect. At elevated temperature, the photoactive compound, PAC, can begin to decompose, and the resin can oxidize or cross-link. Therefore, we choose the lowest temperature and time that achieves solvent removal while avoiding chemical damage. For chemically amplified resists, the residual solvent strongly influences acid diffusion and reaction during post-exposure bake, so soft bake control is especially important. The good news is that CAR systems do not show significant decomposition of the photosensitive components at standard soft bake conditions. The takeaway is clear. Use high temperature curing for BARC and hard mask, use a controlled soft bake for PR to remove most of the solvent, and cool the wafer consistently. With the right recipe, the film is stable, adherent, and ready for exposure. Continuing on, I'll explain why the hot plate and the cool plate are both essential in PAB, how proximity baking works, and how we control fumes and temperature for repeatable results. Older flows used convection ovens near 90 degrees Celsius for about 30 minutes. Modern tools use a hot plate because it gives the best temperature control. State-of-the-art systems hold the mean temperature within plus or minus 0.05 degrees of the set point, and the across wafer uniformity is better than 0.1 degree. Proximity bake is preferred. The wafer hovers about 100 micrometers above a high-mass metal plate. 3 lift pins move the wafer, proximity pins set the gap, and a ring shutter with a gentle air purge stabilizes edge flow. This method shortens bake time to roughly 1 minute and improves uniformity while lowering particle risk. High-temperature films such as BARC, spin on hard mask, and inorganic PR release many fumes. To prevent deposits on the upper cover, we minimize intake turbulence, heat the top cover, and run strong exhaust to carry vapors away. Soft bake for PR runs near 100 degrees Celsius and produces far fewer fumes. Special top cover heating is not required in this case. Temperature must track the recipe through the entire cycle. The heating profile on the right shows fast approach to set point while holding tight uniformity. Cooling matters as well. After the hot plate, the wafer moves to the chill plate, so every wafer cools in the same way. The graph shows how a long delay versus a short delay before chill changes the effective bake time. The takeaway is simple. Use the hot plate and the cool plate as a matched pair. Set a clean proximity gap, manage airflow and exhaust for the film type, and control the heat and the cool with precision to keep the process stable and uniform.